and welcome back. Let's keep going with this definite integral stuff. So from e to 2e of that. So the integral of cosine is sine minus the integral of 1 over x. Oh, you guessed it, ln of the absolute value of x. And we're going from e to 2e. So plug in the upper bound first. So sine of 2e minus ln of the absolute value of 2e. Well, the absolute value of 2e is just 2e. Minus, now plug in the lower bound. So sine of e minus ln of the absolute value of e, or just e. Well, hey, we're going to be able to reduce this. A lot of times when you have ln's and e's together, you got to look for to see if they're going to reduce. So this one here is not going to reduce until I split it and use those properties of logs. So the multiplication becomes addition. And then ln of e, that's just 1. Okay, so distribute this negative across. So that'll be a negative ln of 2. ln of e, that's just 1 again. And then the negative will make a negative. Distribute this negative. So the 1's cancel out. And we have sine of 2e minus ln of 2 minus sine of e. And we're going to leave it like that because we're not using calculators. All right, part F. Uh-oh. How on earth am I going to integrate absolute value of x? We have never done that before. Well, that doesn't mean you're stuck and just go, well, can't do it. No solution. Nope, nope, nope. If you don't have an integration formula to use, it probably means there's another way, and that's to use the graph. Going from -1 to 2. So I got to get the area of each of these triangles. So the little one is 1/2 times base times height. The big one is also 1/2 times the base times the height. And remember, if you want the heights, you got to plug in the x values that go with them. So plug in the -1, plug in the 2, back into your function. So 1/2 plus 2, and that will give you 5 over 2. All right, so in 5.2, all the way back there, we approximated the area under the curve using a lot of different rectangles, sometimes infinitely many. But what if we only used one rectangle? So there's 3 options for us to kind of look at. One is just one rectangle completely underneath the curve, and that would be too little because you've got this extra space that's not covered. The other one is when the rectangle is fully outside the curve. Well, that's going to be too big because now you got a lot of extra. Well, there's one that's kind of in between these two where it's just right. So there's a little bit outside and there's a little bit that's not covered. So again, the graph on the left shows a rectangle whose area is clearly less than the area of the curve between 2 to 5. The middle graph shows a rectangle whose height equals the highest point, so that would be over here, and its area is clearly greater than. So this one that's in the middle, it's in between the short one, it's taller than the short one and shorter than the tall one, and its area is the same as the area under the curve. And the rectangle, it crosses the curve somewhere in there. So this so-called mean value rectangle, which is this one over here, basically sums up the mean value theorem for integrals. So let's see what it says, and then we'll look at what it does. So f is continuous on that interval, or if it is, then there exists a number c somewhere in here, such that the area, or the definite integral from a to b of f of x dx is equal to f of c times b minus a. So all it's saying is, hey, the area that's under the curve is equal to just one rectangle here. This would be its height, and this is the width of its base. Okay, so that'll do it for this video. In the next one, we'll try some examples with this and look at another theorem.